We're going to talk about how to find vector and parametric equations to, in particular, describe motion in a plane. So we have drawn here this yellow line, and this line goes through the point A and B. And what I'd like to do is describe how to get any point in general, a generic point that has coordinates x, y, in terms of the A and the B, what I know there. So because we're going to do this as vectors, we're going to actually try to describe a vector OP, and that's going to kind of act like our point OP, our point P that has coordinates x, y. So we're going to try to describe the vector OP in terms of the A and B. So and I've named the origin O here. So if we look at this vector AB right here, then the claim is that we can get to this point xy by taking a vector from the origin to A, so vector OA, and then add to that the correct multiple of vector AB. So in this case, our value of t that we're going to multiply this by would have to stretch it out that much there. That is, we're going to say that to get to this vector OP, or this point P, we can kind of flow between those. We're going to take the vector OA plus some multiple of vector AB. So for some correct choice of t, that will get us to that point xy no matter where that P is. So you can think of putting P. I put it to the right of B. We could put it further to the right, or in between A and B, or left of A. For any place we place that P, we can get there using this expression right here. So this is known as a vector equation for that line. Now we say the vector AB, that's kind of like acting like the slope. It's telling us the direction. That's known as the direction vector of that line. And you can sort of see, hopefully, kind of the similarity or parallel between point-slope form of a line, where you start at a point and then you go whatever the slope is to generate more points on the line. That's sort of what's happening here. Okay, so let's see if we can look at an example. So down here we're going to find a vector equation of the line through the point 34 and the point 55. So we first need this direction vector, so we're going to find that direction vector AB, and remember we're going to do that tip minus tail. So I'm going to take the 5x value of B minus the 3 of A, and then comma 5 minus 4. So that's going to be the vector 2, 1. So that's our direction vector. We can then start anywhere we like. So we can either start at A or at B. I'm just going to use A. So I'm going to write it in vector form first. I'm going to say to get to any vector AB going from the origin to there, we're going to start at the vector OA going from the origin to point A plus some multiple t of our direction vector 2, 1. And our book won't really use these angle brackets, but they're just going to write it so it looks like points, but we can be interchangeable. And so there is our vector equation for that line that we described. So if we imagine now that if t, so I'm going to change colors here, if the t is equal to time, then the line then shows the position of a particle at time t. So, and we can use t to be 0, we could be t to be positive or negative, either one. Now you can see here that because we have these increments of what we plug in for t, so if t is 0, we're going to start at the 0.34. If t was 1, then in 1 second or 1 minute or 1 hour, whatever t is representing, that particle would have moved 2 to the right and 1 up to where b is. And then if we increment t to be 2, it would jump another 2 to the right and 1 up. So our velocity of that particle is this velocity vector. That's the 2, 1. And since speed is the absolute value of the velocity, our speed is going to be Pythagorean again, is going to be the square root of 5, whatever our units would be, per whatever our time might be. Okay? So there's our velocity and speed of that particle. So let's to the next screen here. So in this problem, we're going to see that a particle has a constant velocity, and it's going to start at the 0.53 at t equals 0, and then by the time we get to b at negative 415, 3 seconds have gone by. So this vector AB that we can find is taking 3 seconds to kind of elapse, to go that distance. So if we take the negative 4 minus 5 and the 15 minus 3, we see this vector is going to be a negative 9 and 12. But that distance that we traveled, that negative 9 to the right, 12 up, took 3 seconds to get there. So our velocity vector, if we want, is going to look like negative 3, 4. That's how far this particle is going to move each increment in time. So each second is going to go 3 to the left, 4 up, another second, 3 more to the left, and 4 up. So that's our velocity vector. And as we saw before, I wasn't going to do both these problems on another problem, but I got a little more ambitious, but that's okay. Here we're going to get that the velocity then, once again, is going to be the Pythagorean theorem. So it's going to be 5. And I don't really have units there, so it's something per second. So there's our velocity, and here is our speed. So what we found here was speed. So the vector equation then, what we can do is say that xy, any point or vector, either way, so whichever notation we want to use is acceptable, we can start either at A or B. I'm going to say start it at 5, 3, and then it's going to be some multiple of our velocity vector, which was negative 3, 4. So there is our vector equation for that line. Now we're going to here we can go from thinking of these as vectors to more kind of particles, and that's what we're going to do here with the parametric equations. So we can see that the x values come from those first coordinates. So that is, we could say correctly that xy is going to be 5 plus, or let me make it a minus because the 3 is negative. We could say 5 minus 3t, and then the y is going to be 3 plus 4t. So that's kind of a condensed version of this. And if we take it one more step and separate these out, we can say x, or if we like x of t, is going to be 5 minus 3t, and y of t is equal to 3 plus 4t. So what we're really doing here is kind of more clearly making this transition from a vector equation, where these are considered to be vectors, to one where this is clearly now particle motion down here. So we're not implying vectors, we're implying a particle moving along a path. And we still have our parameter. It's called a parameter t. And a lot of times we think of that as time, but it doesn't have to be time. It could be something else. And so what we have now, this x of t equals 5 minus 3t and y of t equals 3 plus 4t are known as parametric equations. So let's see an example here. So we have a particle moves along a line in such a way that its x and y coordinates at time t are given by x equals 1 minus t and y is equal to 1 plus 2t. So these are parametric equations that we see right here. We're talking particle motion. So we can now ask the question, when and where does this particle moving on the plane intersect the path of this curve right here? So to do that, we're going to solve the when part first. So we're going to come back here and we're going to solve for t. So if I add the t to the left and subtract the x over, I can say t is equal to 1 minus x. Or I'm sorry, no, I had that right before. Sorry about that. I can actually just plug these in for the x and y. So I'm going to plug in for this x the 1 minus t squared. And in place of the y, I'm going to plug in the 1 plus 2t, and then I'm going to have the minus 1 squared equals 25. So I'm going to create an equation that has only t's in it, which hopefully we can now solve and find out the when. What value of t are these two going to cross paths? So I'm going to square this out. First one squared, 1 minus 2t plus t squared. Let's see, the 1 and the negative 1 are going to cancel each other out. I'm going to take care of them before we square the 2t. That's going to become a 4t squared, still equal to 25. So then the t squared and the 4t squared are 5t squared. And we have a minus 2t. And let's see, we got a 1. I'm going to subtract the 25 over to make that minus 24 is equal to 0. And we're going to try to use our superior factoring skills here. However, you may do this to come up with that. I'm going to do my guess and check. And let's see, I'm going to need a plus and a minus. And let's see, if I go 4 and 6, is that going to work? Let's see. How about, I'm going to go, I think a minus 12 and a plus 2 will give us, there's a negative 12t and a plus 10t gives us minus 2t. So solving each of those, we are going to get t is equal to 12 fifths and t is equal to negative 2. So there is the when part of our question. When is that particle going to cross the path x squared plus y minus 1 squared equals 25? It's going to be when t is 12 fifths and negative 2. And the where, so where are they going to be on the graph? Well, now we're going to plug in the 12 fifths for our x and y. So I'm going to get x is 1 minus 12 fifths. And since 1 is 5 fifths, that's a negative 7 fifths. Y is going to be 1 plus 2t, so that's going to be 24 fifths. And 5 fifths plus 24 fifths is 29 fifths. So one place where these are going to cross is going to be negative 7 fifths and 29 fifths. Kind of ugly there. And then we're going to also use the negative 2. So we're going to get x is equal to 1 minus negative 2. That's a little cleaner. Y is going to be 1 plus 2 times 2, which I think is going to be 5. And so it will also cross at 3, 5. Okay, let's go to a new screen. And we're going to convert parametric equations to rectangular equations, this is known as eliminating the parameter. So there's two different strategies, two different ways of doing that, depending on what our parametric equations look like. If they don't have sines or cosines in them, we're going to try to get t by itself in one of these two equations and then substitute it into the other. And if they do have sine and cosine, we're going to use a different strategy that I'm going to talk about in a minute on that example in the green. So I'm going to solve for the t in that first one. So again, I'm going to add the t to the left, subtract the x to the other side. Then I'm going to substitute that in for the t in the other equation, and that's going to become y is equal to 1 plus 2 times, and then the 1 minus x goes in where that t was. So doing the algebra, we're going to get 2 minus 2x, so you'll see something hopefully familiar, y equals negative 2x plus 3. So this parametric equation, these parametric equations, really are a way of following a path that's going to follow that straight line that has slope negative 2 and y-intercept 3. But remember, the parametric equations are going to have this added information about time. When is the particle at a particular point on that line? Now, for the next one, we are going to tap into, because of the sines and cosines, we're going to use our famous trig identity, our favorite one, sine squared plus cosine squared equals 1. So instead of solving for t like we did in the earlier example, we're going to isolate cosine t and sine t and then plug them into sine squared plus cosine squared t. Let's see what that looks like. So I'm going to solve for the cosine t. So first we'll subtract the 2 over, and I guess that's going to do the trick. And similarly, I'm going to add the 3 over here to get sine of t. Now we can plug those in to our identity, sine squared plus cosine squared is equal to 1. And so we are going to get y plus 3 squared plus x minus 2 squared is equal to 1. And you may recognize that, hopefully, as a circle centered at the origin with, it's not centered at the origin, rather, centered at negative 3, 2, and with radius equal to 1. Okay? Very good.